Well, I'd like to thank Jan for inviting me to give a presentation at the 21 symposium this year. I'm going to talk about our work on cerebellar representation of both errors and internal models. The focus of our work for a number of years has been examining Purkinje cells and their signals and their role in movements. And today I'm going to focus on how we look and think about the representation of internal models and errors in the discharge of Purkinje cells. Concerning internal models, they provide for a representation of the input-output properties of the motor apparatus. A number of years ago, this concept was applied to motor control, and it was applied to many of our thinking about what the cerebellar function is. The initial idea was that the cerebellum operated as an inverse dynamics model. An inverse dynamics model, for example, would take the desired trajectory, for example, of your arm, and it would convert that trajectory into a feed-forward motor command to control an object, again, like your arm to realize a trajectory. Now, inverse dynamics model would be calculating the forces and torques from that desired trajectory. So we hypothesized that if Purkinje cells acted like the output of an inverse dynamics model, they should signal forces and torques and/or muscle activity. Today, when I talk about these recordings, we've been recording from Purkinje cells in the cerebral cortex in regions known to be highly involved in control of movements. For example, on both sides of the primary fissure here, and everything we'll do will record both the high frequency simple spikes as well as the complex spike, which is generated, of course, by the climbing fiber input from the inferior olive. Now, this was the result of the first study, and basically we concluded that Purkinje cells are not modulated by force fields or loads, and that they really do not have the characteristics of an inverse dynamics model. Just very briefly, monkeys were trained to use this robotic manipulandum. They would make track a target moving in a circle. They would track it clockwise and counterclockwise, and we'd apply both viscous force fields at different loads and elastic force fields at different loads. Now, if you look up here, you can see that the hand forces respond as you would expect for viscous and elastic loads. When you go clockwise or counterclockwise, first of all, you see the force increases with the load at the hand, and also the modulation profile of the force is dependent on the direction of the force, just as you would expect for a viscous load because it's directionally sensitive. Similarly, for an elastic load, the forces at the hand scale with the load we apply, but now you can see the forces are position dependent. They don't change direction with clockwise and counterclockwise. They have the same positional characteristics. Now, the EMG activity we recorded from a large number had the exact same characteristics. They showed load increases as we increased, they had amplitude increases as we increased the load, and viscous was directionally dependent. And when we applied elastic force fields, the EMG activity was dependent on position. Down at the bottom was the basic and fundamental result of recording from Purkinje cells. And basically what we found in almost every case, Purkinje cells were not modulated either by viscous or elastic force fields or the magnitude of the load. And again, with that, we basically concluded that the Purkinje cells did not have signals that were consistent with an inverse dynamics model. Now, we also turned our attention to this concept of a forward internal model, as has many of the people who think about cerebellar function. A forward model is interesting because basically it's going to predict the future state of the arm from the motor command and what's going on currently in the arm. And this predictive control has a lot of functionality in controlling movements. Now, one of those things is it has an important expectation for something called prediction errors. So a forward model is generating some sort of prediction called it's referred to as a sensory predictor here, and then it would get feedback about what's actually happening during a movement. So these two signals are thought to combine, and the difference in those signals is what we call a prediction error. And that's a very important signal because it can be used to control, for example, online motion correction, or can be used and is used, we know, for motor adaptation. So from our recordings, does the cerebellum provide for prediction errors? So the test here is that we would think that Purkinje cells would both have predictive signals and feedback signals about the same parameters, and those signals would have opposing action to help in this comparison. Now, some very interesting people said it's tough to make predictions, especially about the future. And that includes no other than Yogi Berra, the past manager of the Yankees, and the very famous quantum physicist Niels Bohr. But I'm going to try to convince you that the cerebellum can make quite interesting projections about the future. Now, we changed our task here. It's a tracking task, but it's a pseudo-random tracking task. So the monkey follows a circle moving about the workspace on the screen. It's moving pseudo-randomly. And the important thing, it allows for lead lag determination of the signals in the Purkinje cell firing. We get better separation of errors and kinematics, and you can get much better coverage of the workspaces that we're examining. So we're going to look at both kinematics and performance error. And the one performance error I want to talk about today is a position error. So position error is the difference. Here's the hand path, for example, as it moves about, and the difference between where the hand path is and the center of the target. So that's position error. It's expressed as both a combination of XE and YE. And then we'll also be measuring position in this space, velocity, and acceleration. Now, one of the first things I would note is simple spikes are clearly modulated by limb kinematics. We've shown that, and others have shown that in other tasks, but that's shown here for velocity. So again, this is our velocity space, because remember, we're working in a two-dimensional space. So this is velocity along the x-axis, velocity along the y-axis. And this is a heat map of the simple spike activity above the mean. And you can see in this corner of the workspace, there's very high increase in simple spike activity. And actually on the opposite corner, there's a decrease in simple spike activity. So again, strong velocity coding. And we show that Purkinje cells encode position, velocity, and acceleration. And they also, importantly, they encode combinations of these parameters. Now, the dogma in the cerebellum has been that the climbing fibers and complex spikes provide air signaling. In this talk and in our work, we've been showing that actually simple spikes have very strong and actually exquisite error signals. And here I'm showing position error, where this is the actual target, this black circle as it moves around the workspace over here. And this is the simple spike firing for a cell in relationship to that target. Now, again, you see this nice coding where along this edge of the target, there's high simple spike firing, and on the opposite edge, there's actually a decrease in firing. So it shows that simple spike discharge encodes hand position relative to the target center. This is position error, and it's a critical signal, error signal, that the monkey uses to perform this task. Now, it was Laurentia Popa in my lab who actually found these position error signals, but then he went on to do something much more interesting, and he looked at the timing. Okay, and this is shown here for a cell. So tau equals 0 is when the error actually is occurring. Now, if you look at these positive taus, you see this simple spike modulation, again, relative to the target with position error, and you might expect that. You would see this feedback or lagging modulation. But what also was very prevalent was this leading modulation in the simple spike activity before the error. So we're going to be talking a lot about this leading or predictive activity. Now, so we have both a lead and a lag, but also notice we have opposing modulation, where the response that's in the predictive part of the for the error is literally opposite of what's occurring in the feedback part. Okay, now when we look at this work, we quantify this using regression analysis. I'll just show this one result here, where this is the regression related to actually XE error for a cell. You see this peak at the leads and a peak at the lags. And here we show the beta, or the sensitivity of that firing, and it shows that at the predictive leads, XE is actually decreasing the simple spike firing, and at feedback timing, the simple spike firing is increasing. Again, that opposing modulation. Now, this is extraordinarily common in all the studies we've done. Something like 75% of Purkinje cells show this predictive and feedback firing with reversal. Now, this slide is to try to convince you how robust this predictive coding is. So this is this prediction, this is a decoding study. On the bottom is the observed error that's going to occur. And what we did is take the activity before that occurred and used a decoding technique. And basically you can see that for either XE or YE, position error, the decoding is virtually perfect. I mean, it's remarkably strong over a range of about 5 centimeters. So the information in simple spike discharge quite well predicts both the performance errors, and what I haven't shown you is it also can do this for kinematics. Now, the fundamental real question is this lagging modulation that we're showing you in these plots, is this really due to the cursor movement? Is it because the animal is watching the cursor? And then the second point is this leading firing. Is this really a prediction of what the hand movement and the position error based on the motor command? So it was Martha Strang in my lab who did this work for her PhD thesis. She used these techniques where she manipulated the visual feedback to test these hypotheses. Now, this is the first test. It involved using a delay. And this is to test the idea, is the prediction really is that predictive firing really a prediction based on an internal model? So normally in baseline, the cursor and hand move together. And again, this is just a cartoon of that bimodal R squared that we get, a predictive component and a feedback component. Now, when we introduce a delay, now the cursor is delayed by 200 milliseconds, in this case, relative to the hand. Now, all the calculations we're doing about the firing are referenced, in this case, to the cursor. So what do we expect? Well, the delay should not alter the feedback error signals because the feedback about the cursor is completely intact. However, the key point is the feed forward error signals based on the motor command will shift earlier because the model should predict based on the hand movements, which are not delayed. So if our hypothesis is true, we should see this shift in the early component and no shift in the feedback component. That's essentially what Martha saw. Here's an example of a cell. This is baseline firing. This is delay. Let's look at lags first. You see that the firing peaks about 400 milliseconds for the lag. It does that in the delay condition. But then something interesting is happening in the feed forward component. So in the baseline, the peak was about 200 milliseconds ahead. But notice now in the delay, the peak predictive firing is shifted to minus 400 milliseconds. And that's exactly what you see in the quantitative data, where this is the peak of the delay and baseline for the feedback, and they're stay in the same position. But if you look at the feedback, or excuse me, the feed forward signal, it shifted over by 200 milliseconds as we predicted. And this is what the population data showed. There was essentially no change in the lag signal in these cells, but for the lead signals, if you applied 100 millisecond delay, the shift was about 100 milliseconds, and if you applied a 200 millisecond delay to the cursor, the shift in the lead was, again, almost 200 milliseconds. So the second thing and second part of this question was to test the hypothesis that the actual feedback modulation is due to cursor feedback. Now here, Martha taught the animals a very challenging task. It's called the hidden cursor. So now when the animal is tracking that target, when the animal actually enters the target, we hid the cursor. So the animal only had feedback when it was outside the target. And the prediction for the firing is pretty straightforward. You would expect a reduction in the feedback signal, but you would expect that the feed forward component would be intact because the animal would still be making its predictions on where the hand is going based on its internal model. Again, that's essentially what Martha saw. So if you look here again at these lagging times, the feedback signals, in the baseline, you see this nice modulation, and importantly, notice the modulation occurs inside the target as well as outside the target. When you hide the cursor, there is no longer modulation inside the target, but you still see modulation outside the target because that's where the cursor is showing up. The strength of the modulation in the lead component or the predictive component remain the same. And again, that's exactly what the population data showed. No significant change in the lead, the strength of the lead activity, but the lagging activity showed a large decrease in the hidden cursor condition. So the interim summary at this point is simple spike discharge signals, both kinematics and task performance errors, and I've talked about position error. Simple spike discharge is both predictive and carries feedback. And what we showed in these last series of experiments is that the simple spike discharge is consistent with a forward internal model, having both a predictive component that is driven, predicting by the motor command, driven by the motor command, and the appropriate feedback component. So I'm going to switch to complex spike activity. And as I already noted, it's been dogma for many years that the complex spike was primarily a feedback error signal. Now that view is changing. A number of investigators are reevaluating that, as we have been. So what I'd like to do first is show you what does complex spike modulation look like with behavior in this pseudo-random tracking task. We use this reverse correlation approach. So here's an example of a Purkinje cell, complex spike. We line the behavioral data up on the complex spike. So we look at for statistical activity, statistical changes in the velocity, for example, velocity before the complex spike. So that would be complex spike in response to that change. And we look for significant changes, for example, in velocity after the after the complex spike, because that would be indication of it. The complex spike is leading or providing a feed forward signal for that change in behavior. So we find using this approach that complex spikes, first of all, modulate with kinematics. And I'll show you an example here for velocity in the middle here. So this is the velocity occurring before complex, feed forward velocity occurring after, that occurs after a complex spike, okay? So this is the leading, this complex spike is leading this velocity signal, and you see this nice modulation. It's a significant modulation change in the velocity. There was no feedback related change in the velocity. So there was no change in the velocity before that complex spike. The behavior is not driving the complex spike. The complex spikes appears to be driving the change in behavior. We have the same thing down here for acceleration, where the complex spike seems to be driving the change in acceleration, not the reverse. Now, up on top is an example of some position encoding, which again, overall was weaker. But again, here's an example where the complex spike seemed to drive changes in position. So it was produced, excuse me, the position was driving the complex spike, a feedback signal. Now, complex spikes in this task do modulate with this position error, but it was basically predictive. So again, this is the the plot of the behavior relative to the complex spikes. You can see here for the, again, a feed forward effect where the complex spike is leading a change in the error, but there was no significant feedback signal. So over the cells we studied, again, I want to emphasize, we saw significant kinematic signal, position, velocity, and acceleration, but we also clearly saw error signals, but they were dominated by predictive signaling, not feedback signaling. So again, I think we need to re-evaluate and about exactly what we think about the climbing fiber input to the cerebellum and what it's doing. Now, a number of investigators have already shown that just normal spontaneous climbing fiber input is absolutely essential for cerebellar function. This is just one example from the lab of Alan Gibson, where they injected canic acid in the inferior olive. These are cats trained to make a movement from a pedestal to a handle. And you can see that the animal gets dysmetric after blockage of the inferior olive. And really, it's hard to make this type of finding consistent with solely an error hypothesis. Climbing fibers must provide ongoing function. And the other thing I would point to is that I think we all know climbing fiber discharge results in a global depolarization of a Purkinje cell. And again, this is an example from Hauser's work showing two-photon calcium signal, where you see these large calcium transients throughout a Purkinje cell. So we came up with the hypothesis that complex spikes possibly could be encoding the encoding of information carried by Purkinje cells, providing a type of state change, if you will. So again, Martha and Lorenz have looked at this. Again, we use this same approach where we now are looking at the simple spike firing related to complex spikes. So everything's lined up on the occurrence of complex spikes in this task. Again, this is just showing one cell. And here's the important point. In this example, what happens is, I'll jump down here to the R squareds. If we're looking at velocity, there's very little velocity coding before the complex spike, but after the complex spike, there's a large increase in velocity encoding. And that you see here, here, and here. So it appears that the complex spike resulted in a state transition in the information being encoded by, in this example, in terms of velocity. Now, again, we observe that for a number of parameters. We observe that for air, for velocity and position. But I also want to emphasize that those state changes could go from increase in encoding a parameter like air here, or decrease in encoding a parameter like air in this for these cells. And similarly for velocity or position. So the complex spike changes the content, and it can either result in an increase in encoding of a parameter or the loss of coding of that parameter. So why and how does this work? So we think that these complex spike changes in encoding may work to help optimize behavior. And this is one piece of evidence that supports that idea. So on the x-axis here, this is the R squared of the encoding after the complex spike versus before the complex spike. So this is the change in the level of encoding, and this is for position error. Now, the largest changes in encoding, or the largest increases in error encoding, actually are associated with the smallest error in that period. So again, the idea is that in this case, for the Purkinje cell shifting its attention to error encoding, it allows it to minimize actually position error in the tracking. So the summary for complex spike discharge is that evoked complex spike discharge is much more than a feedback error signal. And again, I think this is what's emerging from the literature. We see the complex spikes carry error signals. They carry predictive, potentially signals about value. And as we've shown here, kinematic and other predictive signals. Again, climbing fiber in our task have been primarily predictive of both kinematics and position errors. And I think one of the most intriguing findings of the work has been that climbing fibers seem to dynamically control the information in simple spike firing. So again, at this point, our view is that climbing fibers may signal state changes to control the information processing by Purkinje cells. Again, with the idea that it's to help optimize the information that the Purkinje cell needs to work with to optimize behavior. And it's possible, it's a possibility, possibly it's used to select different models as the tasks change. So this is just again, a possible diagram of how this works. We know that the inferior olive, again, as we've said, is providing lots of types of different signals, prediction error signals, in our case, kinematic signals. We know it can other types of error signals. It has spontaneous inputs that when it is activated and goes into the cerebellar cortex, what we've shown is it's changing the information content. Now here again, we're putting it in this idea that maybe it's helping select the right internal model for the task. Again, this is a theoretical construct that we need to do more work on, but we think it might provide a lot of unity to some of the ideas out there about climbing fibers. So with that, I just want to thank both the audience, but also thank the people who have been in the lab and worked on our mini cerebellar projects. I talked a lot about Martha and Laurentia's work, but I'd also have to point out that the early work on the inverse dynamic model was done by Siavash Pasalar and Alex Reitman, and they also helped start us on the forward model work. Angela Hewitt did a lot of work with the Purkinje cell recordings. She had worked with a different task that in many ways came up with the same conclusions that I showed you with the tracking task about climbing fibers, not necessarily responding to errors, but responding to other things and how they encode multiple parameters. So with that, I also will thank my supporters, which have been mainly NIH and a number of grants over the years. Thank you.